Ocean game-based optical and acoustic communication scheduling mechanism for underwater scenario. Abstract. In this paper, we studied the transmission performance of underwater wireless network, where underwater networks users UNU can transmit their data through wireless optical and acoustic communication in a certain range to improve the overall underwater networks. By jointly considering UNU's volume of data transferred and the overall network's transmission performance, we introduced an auction game-based optical and acoustic communication mechanism AGOC. With AGOC mechanism, the base transceiver stations BTS sells wireless optical communications chances through auctions. The users will decide whether to bid according to their own situation, and then the winner could use wireless optical to transmit. Finally, the situation result verify the effectiveness of our proposed algorithm. It also be concluded that AGOC mechanism could improve the overall underwater wireless network performance through reducing the number of UNUs contending for the wireless optical channels. Introduction. The ocean accounts for more than 71% of the Earth's surface, rich in natural resources. As mankind gradually turned the development of Earth's resources to the ocean, it became more and more urgent to solve the underwater communication issues. Underwater communication generally refers to the communication between underwater objects and submarine targets, including submarines, unmanned underwater vehicles, underwater observation system, etc. Underwater wireless communication is an important component of underwater communication technology and is a key support for underwater monitoring, underwater development, and the underwater military struggle. Underwater communication has long been used underwater acoustic communication and wireless optical communication for data transmission, and the two communication methods have their own characteristics. Underwater acoustic communication transmission has long distance and reliable performance, but the disadvantage of acoustic communication is relatively low transmission rate, large delay, and high power consumption. In contrast, underwater communication based on visible light has a high transmission rate, strong anti-interference ability, high security, and low power consumption, but its transmission distance is shorter than that of underwater acoustic communication. First, based on the characteristics of two communication methods, we can use their respective characteristics to forward the corresponding data. Underwater acoustic communication can be utilized to carry out data with the low volume between static nodes, such as signal information transmission and voice information transmission. The wireless optical communication can carry on the large data transmission between the mobile node and the static node, such as the image data transmission and multimedia communication functions. With the rapid development of land communication network technology and rise of global ocean exploration, the research of underwater communication network technology has become another hot topic. In underwater communication network, we will place a number of low power, low cost with a certain communication coverage area, BTS, in a sea area, which constitute our wireless network communication network. UNUs within the BTS coverage area can send real-time data to the BTS. BTS collects the information from the node to realize the transfer of the information. After the collection, the BTS transmit the information to the software-defined network controller SDNC through optical fiber, and then the data will be transmitted by SDNC to the surface observation vessel or communication buoy. Which can complete the underwater information transmission 3 to 5. Therefore, it is of great significance to study the transmission characteristics of underwater channel in marine environment. Search for underwater high-speed and effectiveness wireless communication technology, and build corresponding underwater network communication system. It provides a technical way for human beings to explore, develop, and utilize marine water resources, which makes human being able to understand the research, exploit the ocean. In this paper, we proposed the AGOC mechanism to improve the performance of underwater communication network, we jointly consider UNU's volume of data transferred and overall network transmission performance. 6. In auction game-based optical communication mechanism, BTS will sell wireless optical communication opportunities to transmit data every day, every T period, according to the bidder own situation that they can send the maximum data traffic volume decided whether to bid. Therefore, the UNUI who has the most of data volume can obtain a high transmission rate due to the AGOC mechanisms. 7. By reducing the number of UNUs contending for wireless optical channels, the problem of congestion in underwater communication network can be alleviated. Thus, the performance of the underwater communication network can be improved. The remainder of the paper of this paper is organized as follows. In section 2, we first introduce the system model. Problem formulation is proposed section 3. The proposed auction game-based optical communication mechanism is provided and analyzed is section 3. Section 4. While the data traffic transmitted through wireless optical is evaluated in section 5, the simulation results verifies the effectiveness of our proposed algorithm in section 6. System model. The framework of underwater wireless communication network is demonstrated in figure 1. In this underwater network, there are some equipment placed in it to cover underwater communication area. As it is shown in this picture, lots of hexagonal cell is existing in which a base transceiver station is in the center. In each hexagonal cell includes various users such as unmanned underwater vehicles, drivers, submarine, and so on. Underwater communication users can transmit signaling information, voice message, pattern information, and fulfill their data information services through acoustics or optimal communication. The user who wants to transmit his message to another should communicate to one base transceiver station first, and all base transceiver stations are linked to software-defined network controller (SDNC) through optical fiber. The SDNC can be linked to the water information collected platform through a transducer, which can realize the underwater message transmission 8 to 9. The transmit model is demonstrated in the figure 2. We consider that acoustic communication is covered to the whole hexagonal cell. All the users can transmit their data through acoustic in it. The value of data traffic transmitted user acoustic to communicate unit price is DA. The wireless optical communication is the focal point is the underwater network. Denoted D0 is the volume of data traffic transmitted using the wireless optical per unit time because the distance of the optical communication is limited. It is the center of the hexagonal cell network. We take BST as the center. The farthest propagation distance of optimal communication is reduced to draw a circle. In the area covered by the circle, the user can communicate to the transceiver stations BTS carried out by wireless optical communication, which can achieve a large capacity data transmission with freight rate, low latency, low power due to two optical factors affection, namely photon absorption and the photon scatter existed. The propagation speed of the optical communication will change with the distance of the propagation, so we divided the circle into several discrete regions SI. I equal 1 to n, such that the users in each region have a different optical transmission rate which are denoted by V1. Additionally, with the width of each region denoted by DI. So the instance optical transmission data rate of underwater network users UNUSI in the region SJ can be defined as in which rho is optimal communication throughput efficiency factor. W is the number of UNUs within the coverage area of the circle. QW is decreasing function with W, denoted optical channel utilization function respectively. The number of UNUs within the coverage area of the circle can be calculated by this, where the K and I equal 1 to n sigma are underwater users density in the hexagonal cell and then radius of the circle. The channel spectral efficiency is denoted by sigma bit hertz, which is considered to be uniformly distributed in the range sigma min to sigma max. UNUs are located with W bandwidth for acoustic communication, so the expected data rate of acoustic communication is VA, WA, and the transmission rate BI equal DI per V, where V is the average of UNU's speed. For underwater network users, high bandwidth and low latency can be achieved by wireless optical communication, which can improve the performance of network transmission, although the users want the networks to transmit their data immediately. It is possible to postpone a certain of time to deliver some non-urgent data information, such as program updated, uploaded, or downloaded video data until the users enter into the optical communication area, but the delay cannot be too long, otherwise it will give users a poor transmission experiences. 10. Therefore, we use a periodized transmission-based information significance. In the underwater wireless networks, each information that delivers to other places is assigned by the priority, where 1 is the highest priority and 2 is the best. When a UNU I want to transmit its data, the BST will search for data which want to transmit in each hexagonal cell with the highest priority 1. If there exists one data in hexagonal cell with 1, the BTS will forward the information first through acoustic communication. Otherwise, the BTS looks for data in hexagonal cell with row 2. If exists, it means that the data can delay certain time to transmit, and put the function pt, which reflects the volume of data the user is willing to transmit with delay t. When t is 0, the data traffic of user I is transmitted totally through acoustic communication, thus pi equals 0. dA zi, where zi is the price of transmission data. Problem formulation with the goal of achieving better underwater communication performance. For example, maximizing the amount of data transmitted by the underwater communication networks. The issue is to schedule the UNU with the most data traffic relayed by wireless optical. Each data place BTS UNU can transmit by wireless right to achieve data transmission programs in a certain range of BTS. In this section, we give the formulation for data transmitted by optical maximum program. The objective is to maximize the total data transmitted quantity in underwater communication network. The problem of how to select the UNU with the most data needed to relay can be induced into the amount of data that UNUs can transmit in the wireless optical unit prices program. We use Yij to indicate the amount of fj that UNU I want to relay. Let S U be the number of app and the UNU, and extract the data traffic based formulation as follows. Data traffic based formulation denoted variable xij to decide whether UNU is implementing fj's transmission. xi1 UNU I is performing fj's transmission, 0 otherwise. Data traffic based formulation is shown as follows. Auction game based optical and acoustic communication mechanisms. Wireless optical communication can provide better transmission quality quality than acoustic communication. In this part, we introduce an auction game in which the BTS sell wireless optical communication opportunities through auctions. The theory of the AGOC as follows. In an arbitrary auction, there are one or more bidders. The BTS sells optical transmit opportunity in the area of each circle. We users can decide whether to bidding according to the situation. There is only one person can win the end of the auction who can use wireless light to transmit data, while others will only use acoustic to transmit. In order to adapt to the dynamic changes in the underwater network situation, the auction is repeated from the time to time. The auction mechanism is a hexagonal cellular network covered by each BTS is the same. Auction may create additional delays but can be tolerated by the auctioneer. 11. For an auction, the auction begins at T and the delay of the current data transmission is T prime. So the total volume of UNUI should transmit her for current data can be calculated by where Ki and Ri are the prices already costed through wireless optical and the data already transmitted through wireless optical. Denoted the auction intervals is T. Thus, the expected volume of UNUI can deliver by the optical expressed by where rho I is a straightedge of UNUI. For example, rho I indicates that UNUI bid at the D0 and the rho 0 indicates the UNU. I does not bid the BT. Is the prices that data traffic transmit through wireless optical from T to T plus T is the remaining price of transmitting the current data UNUI. Accordingly, mean BIT TBZIR is the expected price that can be transmitted through wireless optical during the T plus T. G is the least amount of data that UNUIs should transmit if application is delayed from T to T plus T. We can obtain that GIT equal max HIT minus ZIT minus ZIT prime plus T. Lambda is a positive value to compensate the error in the prediction. Based on the above formula, we can obtain the maximum data. The flowchart of AGOC. Traffic volume at the UNUI can be by. Denoted Q0 is the BTS data traffic received through optical transmission, and it can be expressed by Q0 equal T.DA win, where DA win is the volume data traffic when the auction concludes, and the flow chart of the proposed AGOC is shown in figure 3. Before the auction, we set the volume of data traffic transmitted used wireless optical per unit time 0 as 0. During the auction process, according to the bidder's own situation that they can send a maximum data traffic volume decided whether to bid, and the amount of data for each auction increases in the size of P than before. The size of the data obtained by the new bidding will be reported by the BTS to the UNUs within the circular data. If UNUIs find that the maximum amount of data which can transmit is larger than the current bidding, it raised a new bid until only one person wins the auction. The winner can use wireless to transmit data and others fulfill their data transmitted through acoustic until the subsequent auctions start. Thus, when the auction is concluded, the expected volume of UNUI can delivered by optical QI equal DA mean BIT T ZIR minus D0 dot T minus GI T square comma T minus lambda. In order to reduce the contention in underwater wireless communication network, we expected the overall performance of underwater data transmission as high as possible. AGOC mechanism can improve the overall transmission performance. by mitigating the contention of underwater networks. By auction, only one person can win the auction, using wireless optical for data transmission, while others can only use underwater acoustic communication for the transmitting. Therefore, the competition of the wireless optical communication channels is decreased, and the underwater wireless communication networks performance can be promoted. 5. Data traffic prediction based on transmitted data model and the AGOC mechanism described in above selections. We will evaluate the data traffic transmitted through wireless optical in this section. In this section 2, we divided the circle into several discrete regions which describe the state of UNUI. Here we use continuous time function xt to describe the zone of UNUI at time t, where xi is S0, S1, Sn if the start of the zone is P and the next zone is Q we defined, where rho denoted the LPQT, rho PQ, KPQT, 1 minus E minus BIT, Q equal P plus 1, where rho denoted the limiting probability of the delivery from P to Q, and KPQ is the time to stay in state P. Considering Q is the next state, we can conclude that if Q not P plus 1, rho PQ equal 0, so LPQT, and if Q equal P plus 1, like this. As can be seen from the moving the model, UNU can only move from SP as P plus 1, so LPQT 1 minus E minus BIT. Additionally, we define the transition probability of X as follows, where alpha PQ is an indicator and 1 minus KPQT alpha PQ is the probability that UNU's position changes in time. The probability that UNU's transition from P to P plus 1 is in time L is LP P plus 1 L, which can be expressed as P plus 1 L, L P plus 1 L minus P plus 1 L minus 1. From above the total volume of data traffic transmitted by wireless optical, if the UNU's I's initial state is SP and the final state as Q, can be expressed as like this. Simulation result. In this section, we evaluate our proposed AGOC mechanism and demonstrate the performance of transmitting data through wireless optical and the average service delay. The simulation is carried out in a 2.0 km times 2.0 km region of the coastal area of Dalian. The SDNC is placed the center of the coverage area, and the BTS are randomly deployed within the area. Each BTS has a certain coverage, and then their coverage area may overlap, but that will not cause a large impact on data transmission. We assume that UNU can transmit data through wireless optical immediately without time consuming on accessing approval. In the simulation, DA is set to 1 megabyte. We consider W equal 2 kHz and rho max mean 0.2. So the rate of underwater acoustic transmission is 2 kilobyte per second. The price of transmission data randomly chosen from $20 to $50. We set the wireless light transmission area is divided into 7 parts. Each region is set as follows: D1, D2, D7, 57, 25, 15, 50, 54, 15, 25, 15.7, and the average UNU speed is set to R, 40 km per hour. The auction intervals and delay interval are set to 10 seconds. At the same time, we take CL and then UD mechanisms to compare. The former mechanism UNU can flexibly select the transmission mode. If UNU in the area can transmit data through wireless, it will choose wireless optical, otherwise it will choose acoustic transmission. The later mechanism, the UNU constantly delay their data to wait for wireless optimal transmission opportunities. The simulation runs for 10 hours and the result averages over 5 runs. Figure 4. Total traffic transmission. Figure 5. Average transmitted delay. The performance of the proposed mechanism is shown in Figure 4 and Figure 5. Figure 4 shows the total traffic transmission by wireless optical. It can be seen that the volume of data traffic transmitted in AGOC mechanism is much more than CL and UD mechanisms. Figure 5 shows the average transmitted delay. It can be seen that the transmit delay under the AGOC mechanism is lower than CL and UD mechanisms. In the CL transmission mechanism, if the majority of UNUs are moving with the range of wireless optical transmission, the channel will be congested, reducing a low transmission rate, so the amount of data transmitted through wireless light is few. If the majority UNUs are moving outside the scope of wireless optical transmission, the UNUs have no chance to conduct wireless light transmissions. In the UD transport mechanism, if the UNUs are continuously delayed for wireless optical transmission until move in the wireless optical transmission range, the data that UNUs are willing to transmit through wireless optical will be reduced. Because the transmission delay may be too long, but AGOC mechanism, the followed-up problems can be solved well. The channel contention and time delay are further alleviated. Conclusion. In this paper, communication scheduling mechanism for underwater scenario is proposed. Under the water, we place a set of BTS to cover the area that we implement our test. All BTSs are linked to SDNC by fiber optical, and we theoretically investigate the data traffic transmitted by wireless optical and then transmission delay based on AGOC mechanism. With the proposed AGOC mechanism implement, the UNU who has the most data traffic needed to transmit can use wireless optical to deliver, so the overall performance of the underwater networks will be optimized. While win-win situation is created for both UNU and the underwater networks, we simulated the UNU with the data traffic to deliver using the AGOC mechanism and other using transmission mechanism to compare, and deliver total traffic transmission and average transmitted delay. The results validate the analysis and show the effectiveness of the proposed mechanism. The proposed mechanism outperforms existing mechanisms. For our future work, we will study other transmission mechanisms that not only one UNU could use wireless optical to deliver combined with existing AGOC mechanism, which can improve the channel utilization as much as possible.